Oh, so the reason that was up is I wanted to make sure everyone was aware that there does exist a schedule for the Math Retreat, and hopefully everyone can make it to some of the Math Retreat events. I guess the hour between 3 and 4 isn't even necessarily a single event, so the fact that this class is canceled on Monday doesn't necessarily mean you definitely can make it. Hopefully everyone can make it to something. So let's think about what kind of we started talking about a little bit last time. We started talking about extensions of functions. I said, well, and I think I'm going to put this definition down. So if you have U a subset of V and F a map from U to R and G a map from V to R, such that F and G are the same function as long as X is in the smaller set, then I'll say that G extends, or is an extension of F. And maybe a picture is a good way to see what this is saying. So this is saying maybe you have some small set U and some slightly bigger set V. Then if you have some function defined on U, then another function G defined on the bigger set V is an extension of F if G agrees with F on a smaller set, and otherwise takes whatever values it wants. So that's all an extension means. It's an extension of the definition of F onto some bigger set. So the question to ask is, if you start with some continuous function and some slightly bigger set than the domain of that continuous function, when can you find an extension of domain? And we saw last time one example when you can't. If you start with the function f of x equal to the cosine of pi over x, well, that's defined everywhere away from 0. But there does not exist a continuous function which extends that continuous function. Because if you had such a continuous function, then it would have to take some value at 0. But for reasons of limits, somehow that value would at the very least have to be 0 and would have to be -1 and 1 simultaneously. But it can't be both. This is an actual honest-to-God function, so this function has no continuous extension. Let's see one example where there is a continuous extension. Let's let f from 0 to 1, open interval from 0 to 1, be given by f of x equal to x squared. I claim there exists a continuous function defined on the closed interval from 0 to 1, which extends this function. So I want to come up with a function. I just need to show that a function exists. So that means I get to, if you need to show that something exists, one way to do that is by giving it a name. So let's define a function g on the closed interval from 0 to 1 to all of the real line. What formula would you like to use? Let's see, this function has to be equal to x squared while things in the open interval from 0 to 1. So what function would you like to take on the closed interval from 0 to 1? How about x squared? That seems reasonable, right? And let's not try to come up with an epsilon delta proof of continuity, but tell me, why is that continuous?
Because it's Cauchy.
Sequences are Cauchy.
Oh.
Well, I mean, in some sense, we've proven that it's continuous. I think a few times. think you have actually given an epsilon delta proof, but maybe here's the like quickest, most convincing way. Is that a product of two continuous functions? So maybe there's a reason. If you want to make the argument fun, authority that we've already proved it. Well, I know evidence. Okay, so but now let's show why this is an extension of f. And let's see, so that means that we need to show that f of x is equal to g of x for all x in the smaller domain. And I mean, I think this is one of the things that's like easier done than said, because you already know why it's an extension of f. They have the same definition. Period. So let's go through the motions just so we get a feel for what the definition even means. So let's consider any x in the open interval from 0 to 1. I need to show f of x is equal to g of x. So for an x value in this open interval, tell me, what is f of x? X squared? On the other hand, what is g of x?
X squared.
Also x squared. So g extends f. Cool. So let's just think about the one example and one non-example we have. We've thought about this example where f of x is x squared. We've found that g of x equal to x squared extends into the closed interval. And in fact, that's about the only choice you would have. I couldn't define it at 0 or at 1 to be anything other than those values and hope for it to be continuous. And if you like, that's because there was stuff where you know the value of f of x, and so g of x really close to those points. So you didn't have any options. And it was the same thing that happened when we thought about the cosine of pi over x. We thought about evaluating it at a bunch of points and realizing that any continuous extension would have to be 1. Evaluated at some other points and thought any continuous extension would have to be negative 1 at 0. And that's how we got the contradiction. So it seems like this question of extensions of functions, it's really important that you try to, something interesting happens when you try to extend the domain to a point not in the domain, but which has things that are really, really close to it in the domain. That's the place where it's interesting to try to extend the definitions of functions. What types of points are those? If I give you a point, and for every delta bigger than 0, there's stuff really, really close to that point. It's a limit point. So it looks like the interesting place to try to extend definitions of continuous functions is over the limit points of the domain. And that makes sense, right? If you try to extend it to a point that's not even a limit point, well, then it's like nowhere near the domain of the function, so you should just be able to extend it to be whatever you want at that point. So there's nothing interesting going on. So I think I'm going to blow by this example with the sign with a g of x, because it's the same example again as the cosine of pi over x. The same thing happens. Let's try to prove a theorem. And before we try to prove a theorem, let's try to think about where we want to extend these functions. We want to extend these functions to a slightly bigger set, which is the original set, and maybe together with all of the limit points of the original set. And so I'll call that set the closure of U. And, well, in fact, there's a better definition of the closure that seems more self-contained. So the closure of a set U is given by the set of all real numbers, such that for every positive number delta, there is a thing in the original set U, which is within a delta of the point x that you would like to be at the closure. And that's like, what that's saying is those are points where there's stuff arbitrarily close to that point in the domain. So yeah, that should be the type of point that you should try to evaluate a limit. So let's prove that these two definitions are actually consistent. But on the one hand, this is the type of point that we would want to try to ask whether you can extend the function to. There's a self-contained definition. Let's prove that they're actually equivalent. Many people recognize this from maybe a benchmark problem on your. Yeah, right. You prove that it's closed, I think. Which it better be, because I'm going to call it the closure. So here's a proposition. For any set U, the closure is given by the union of U together with all of the limit points of U. And let's try to prove that. How do you show two sets are equal? Double containment. Let's go through the motions. So let's prove that the closure is contained in the union. Well, let's do it. So on the one hand, let's consider any x in the closure. If that x already happened to be in the set big U, then I'd be done, right? Why would I be done?
Definition of unions.
Definition of union. It would follow if x were in U, then it would certainly follow that x were in U together with the set of all x such that x is a limit point of U, which is exactly what we want to show, right? Right, you want to get it to be in U. So we may as well assume that x is not in U. So right now we will assume that x is in the closure of U and x is not in U. And I guess we better show that x is in this set. So we need to show that x is a limit point of U. And let's try to do that. Who remembers what the definition of a limit point is? Is a limit point of a set U if.
Does it start with for every delta greater than 0?
Yeah. And there's nothing special about a name, but I think delta is the right choice for our purposes right now.
There exists x's in U such that.
Let's make it a U.
Okay.
Because x already has a job.
Such that 0 is less than the absolute value of x minus u less than delta.
Yeah. So since this point x, so that's what we need to show. We need to show this. So if we want to prove that statement, we'd better consider any delta bigger than 0, and then demonstrate the existence of some u such that that happens. Well, but let's see. By assumption, x is in the closure of U, and there's the definition of the closure. And this delta is positive. So what can we conclude since x is in this set? Well, the stuff to the right of that colon should be true, right? That's what set builder notation means. So we know that for every positive number delta, there's something in U with the absolute value of x minus U is less than delta. That's almost what we want. That's almost everything. So since x is in U bar by assumption, the definition of U bar concludes that there exists some U in U with absolute value of x minus U less than delta. And now I just need 0 is less than absolute value of x minus U. Why should 0 be less than the absolute value of x minus U? Let's try to punch this around. So 0 is less than the absolute value of a difference. That just means those two things aren't equal. So tell me, why can't x be equal to U?
Except is not in you.
X is not in the set big U. Little u is in the set big U. Very good. As X is not in the set big U, and little u is in the set big U, X is not equal to U. So 0 is less than the absolute value of X minus U is less than delta. Thus, X is a limit point of U, and so X is in the set U together with all of the limit points of U, and we get U bar contained in the union we want it to be contained. How do people feel about that argument? I go pretty okay? So there was this I guess there was the step at the beginning where I said, well, let's assume that the point X isn't in the set big U. And on the one hand, that's not a harmful assumption, because if X were in U, then you would be done. But maybe it wasn't clear why that would be useful. But upon finishing that proof, it is clear why that was a useful assumption to make. Sometimes when you try to write a proof and you need an assumption, just make the assumption, then go back and try to fix the proof to account for the assumption. That's how this one went. Let's do the other direction. Let's prove the reverse containment. Let's consider any X in the set U together with all of the limit points of U. Then one of two things must be true. Either X is
In U.
in U, or
It's a limit point.
it is a limit point of U. So let's deal with the case that X is in U. Now to get X to be in U bar, I need to show that for every delta bigger than 0, there exists a U in big U such that absolute value of X minus U is less than delta. So let's consider any delta bigger than 0. I need to come up with a choice of little u, which is really, really close to little x. So if X is in the set big U, can you think of something in big U that's really, really close to X?
X.
How about X? Then, absolute value of X minus U, well, that's X minus X, which is 0, which is less than delta. So we're good. So that was the dumb case, though, right? Let's do the actual bit that might have content. On the other hand, let's suppose that little x is instead of a limit point of view. We'll consider any delta bigger than 0. And I need to come up with an element of u such that the absolute value of x minus u is less than delta. Well, but this point x is a limit point of u. So this is true. And I've already picked a positive number delta, so what can I conclude because x is a limit point of u?
There exists a U such that 0 is less than all that stuff.
Why does that imply that x is in the closure? Nope. Why does that imply that x is in U bar?
The U bar is closed.
Well, I mean, I guess you proved that, but we didn't assume that x is a limit point of U bar. We assumed that x is a limit point of U. So to get x to be in U bar, we need there to exist a U in U such that everything except for that 0 is less than holds. But we do have that, right? Because we know that that's true and 0 is less than that. So we just already have it. So in particular, there exists a U in big U such that I'll just not write the 0 as less than. So by definition of U bar, x is in U bar. How do people feel about that? Good. So, the set U bar, the closure of the domain of a function, is the right place to start asking about extensions of continuous functions. If you want to extend that continuous function beyond U bar, you need to start thinking about things like the Tietze extension theorem. Let's see, in Kieran's class, did you get to Tietze extension theorem for topological spaces?
I don't think so.
Okay. One of the semi-options for the final project, which I haven't finished writing my end yet, is proving the Tietze extension theorem. It'll show up, don't worry. So let's suppose that, so here's the theorem that I'm going to try to prove. Suppose that you have a function which is continuous, and which has the property that at every limit point of view, the limit of f of x exists. So let's draw a picture of that. So you have a function defined on some domain, and you have some limit point which is not in the domain, where the limit of this function exists. If you were to want to come up with a continuous extension of this function onto the yellow set together with its one limit point that it doesn't contain, like, you know what value you would want it to take at that yellow point, right? We want to just like take that value. We want to fill in that domain. So that suggests somehow that as long as you have a candidate value to take, a limit at every point where you could take a limit, you can try to extend this function to the closure of its domain. And you even know how. You would want to just set g of x to be the limit of f of x. So that's how we'll prove this theorem. Theorem 3.7.9. If you have a continuous function which such that at every limit point of the domain, the limit of f of x exists, then there's a continuous function to the closure of extending f. Well, but we have one class of functions which have all of their limits defined, right? If you have a continuous function, and you take a point in the domain of that continuous function, then the limit of that uniformly, if you have a uniformly continuous function, then the limits of that uniformly continuous function always exist. So you satisfy all of the hypotheses of 3.7.9, so you should get the same conclusion. So here's a corollary. Suppose that f is a uniformly continuous function. Then there exists a continuous function, g, from the closure to our extending f. So let's, I don't know, let's go through the walk of proving the corollary, assuming the theorem. So let's prove corollary 3.7.10, assuming theorem 3.7.9. So let's suppose f from u to r is a uniformly continuous function. And here's how we'll do it. Let's just try to check that all of the hypotheses of the theorem are satisfied. And so the conclusion of the theorem will happen. If f is uniformly continuous, does it automatically follow that f is continuous? Yeah, right. Uniformly continuous just says the choice of delta can't depend on x. There still does exist a choice of delta, so it is in fact still continuous. Consider any limit point p of u. Have we proven that the limit as x approaches p f of x exists at every limit point of u? Do you remember the name / number associated to that theorem? Where's the note back from last time? So in 3.6.12, we said if u is a subset of R, and f is a uniformly continuous function on u, then for every limit point of view, the limit as x approaches p of f of x exists. So in theorem 3.6.12, we prove that the limit of f of x exists. So all of the assumptions of theorem 3.7.9 are satisfied. This function is continuous, and for every limit point of the domain, the limit of f of x exists. So that means the conclusion of the theorem should hold, assuming that the theorem is true. There exists a continuous function, g, from u bar to r, extending f. People feel pretty okay about that? So let's prove the result now. Let's prove theorem 3.7.9. So let's suppose that f from u to r is a continuous function, and that for every limit point p of u, the limit as x approaches p of f of x exists. I'll now just try to come up with what the definition of g of x should be. And remember, I want to define g of x on the set u bar, the closure of u. Now, there are two different types of points in the closure of u. There are the points that are in u, and there are limit points of u. So I just need to come up with a definition in each of those cases. So in the case that p is a point already in u, what do you think g of p has to be equal to? If g actually extends f. Has to be the same as f of p. On the other hand, if p is a limit point, then by continuity Gesundheit, you would want g of p to be the same as the limit as x approaches p of g of x. But there are x values really, really close to p that are in u, not just u bar. So that means that the limit as x approaches p of g of x should be the same as the limit as x approaches p of f of x. Wait, then there's the definition that I should take for g of p. So on the next page, I'll define g in terms of cases. In the case that the point where I want to evaluate g is already in u, I'll set g of x equal to f of x. G of p equal to f of p. If p is a limit point of u, then I will define g of p to be the limit as x approaches p of f of x. Fair enough? So I have my candidate. What do I need to show about this function g? Well, what does the theorem require this function g to do?
Extend f.
It needs to extend f and be continuous. I guess another thing I'll worry about, which maybe isn't even obvious that you do need to worry about, this is that it'll actually be a function. This is a case-wise function, but is it possible that there's a point in u which is also a limit point of u? Yeah, it's totally possible. So then you have two different definitions. They better agree. If this is even going to be a function. So let's even start with that. Let's verify that g is even a function. And all that's going to take is the fact that f is continuous. So let's see, let's let p be a limit point of u, be a point in u, which is also a limit point of u. So something which satisfies both of these conditions. I need to see why f of p should be the same thing as the limit as x approaches p of f of x. So why should that happen? Because this function is continuous. And we prove that a function is continuous at a limit point of the domain if and only if that equality happens. So since f is continuous at p, and p is a limit point of u, it must be that the limit as x approaches p of f of x is equal to f of p as we need. Nice. Okay, so it's actually a function. Well, I guess I'm even blown by why does this function extend f? Why does this function g of x extend f of x? let's see, for a point in U, what is g of x equal to?
That's the point.
F of that point, and that's exactly what you need to do to be an extension. Okay, so there's no content there. Let's prove that this sucker is continuous. And since that's the remainder of this packet, maybe you believe that this part of the proof will have some content to it. And I mean, it's believable though, right? Like the picture says it has to be true, except that there are complicated offsets than that set. Let's try to do it. So we're going to check for continuity. So let's consider any point in the domain. Let's consider any epsilon bigger than 0. I need to show that there exists some delta such that for every x in U, if the absolute value of p minus x is less than delta, then the absolute value of g of p minus g of x is less than epsilon. That's what I need to do. So my choice of delta is allowed to depend on the point where I'm checking for continuity. And there are like two different types of points in the domain. There are the points that are in U, or points that are limit points in U. So let's break down our argument into cases. Either this point P is in U, or this point P is a limit point of U. Everyone feel pretty okay so far? Nice. Okay, so case one, let's suppose that P is in U. In the case that P is in U, what is G of P equal to? F of P. Now this function f is continuous at P. So that gives me an avenue to get a choice of delta. Maybe it won't be the right choice of delta, but let's try it first. There exists some delta bigger than 0, such that for all x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. And maybe you can tell by the way I phrase this that maybe there's going to be some like epsilon over 2 argument showing up. And I'll try to keep that epsilon in. You can't tell that it's green, but you can tell it's not red. So I think it's an okay color choice. Okay, so now let's consider any x in U and assume that the absolute any x in the closure of U, and assume that the absolute value of x minus p is less than, well, I get to put any positive number I want there, right? For now, I'll put a delta there. Maybe that control won't be good enough. But if it's not, and I discover it's not good enough, then maybe I'll even be able to tell why it's not good enough, and so I'll be able to fix it. So there are two cases. Either x is in U or it's a limit point of U. And no, I don't want that to be red. I want another color. There. So now there are 3 colors going around: red, green, and purple. So let's try it. So either x is already in U, or x is a limit point of U. And so now we have two subcases in this big case. Let's think about case 1a. Let's suppose that x is in U. If x is in U, then what's g of x equal to? F of x. And my goal is now to get absolute value of g of x minus g of p to be less than epsilon. And let's see why that should be true. In the current case, in case 1a, what's the absolute value of g of x minus g of p equal to? F of x minus f of p. Well, in the easiest part of the easiest case. Good. And let's see, this x minus p, right now it's less than delta, which is purple, which in turn is less than or equal to delta. So what does our choice of delta tell us about the absolute value of f of x minus f of p?
It's less than epsilon.
It's less than epsilon by, I guess, this line? and that epsilon is an epsilon which is in green, epsilon is indeed less than or equal to epsilon. So we'll find we don't have to make any revisions to our guesses yet. On the other hand, case 1b, let's suppose that x is a limit point of u. If x is a limit point of u, then what is g of x equal to?
The limit of f of x as x approaches b.
Well, you use the wrong variable names. It's certainly the limit of f of something as something approaches x. So I just need another letter, so I'm going to introduce a new letter called y. It doesn't matter what you call it. G of x is the limit of f of some variable name as that variable approaches x. Aha. So there's a limiting statement. So I should be able to do something with that. And now let's start with this. This parameter x. So yeah, let's unravel this limiting statement. So g of x is equal to the limit as y approaches x of f of x. And this parameter epsilon that we have right now is bigger than 0. So there should exist some positive quantity delta, so that for every y in u, if 0 is less than the absolute value of y minus x is less than this positive length delta, then the absolute value of f of x minus g of x is less than any small number we want. Epsilon. So let's see what that means. So let's draw a picture of how this argument is going to go. So g of p right now is equal to f of p. I would like g of p to be close to g of x. And right now, x is not itself in u. Instead, it's a limit point. So g of x is literally equal to the limit as y approaches x of f of y. But that means g of x, I can get that as close as I want to f of y. But let's think about this a little bit more. Is this y supposed to be close to p? Well, it's close to x, right? Is x close to p? So y is also close to p, so we should be okay. So let's keep track of all of those things. So let's see. So since this point is an accumulation point, I can find y values in u, which are as close as I want to x, without being actually equal to x. So there should exist some y in u such that 0 is less than the absolute value of x minus y is less than any positive parameter we want. I don't know. This delta 1 seems important. And I don't know. Oh, no, that delta 1 should be in red. What are the things that I'm not going to revise? And I don't know. We have this other delta floating around. Let's put that bubble delta there too. Now let's try to control absolutely everything that we can. So I eventually want f of y to be close to f of p. This function is continuous at p. So if I can get y to be close enough to p, I can get f of y to be really close to f of p, which would make me happy. So let's try to phrase out how close is y to p. And we'll walk this out from the inside out. So according to this picture, I want y to be close to p. Can you think of a single thing right now that's simultaneously close to y and close to p? X. Right, y is, by the very way we're building it, really close to x. X is, by the way we're building it, really close to b. So y minus p, let's write that down as absolute value of y minus x plus the absolute value of x minus p.
Can you pull it down?
Oh, yeah. And let's see what controls we have over these. What's the bigness of the difference between x and p? It's delta, right? Absolute value of x minus p right now by assumption is less than delta. And the absolute value of y minus x is also less than delta. But if I hope to get the absolute value of f of y minus f of p to be less than epsilon, I need the absolute value of x minus p to be less than delta. Right now I have the absolute value of x minus p less than 2 delta. What's the solution? How can I fix this? Cut them each in half. Divide everything by 2. Divide all the deltas by 2. And this is why I tried to be careful with my color coding. So I'm going to try to divide all of those purple deltas by 2. So, early in the proof, I'm going to assume that absolute value of x minus p is less than delta over 2. Is delta over 2 less than or equal to delta? Yeah, so now this line that originally just seemed silly is now just correct. I guess it could even be strictly less than, but we didn't need strictly less than. Let's also conjure up the existence of some y in use. It's the absolute value of x minus y is less than the min between delta 1 and delta over 2. So now these two deltas are divided by 2 equals delta. So by the continuity of this function f at p, we get the absolute value of f of y minus f of p less than epsilon is green. Very good. But let's also, I know I'm going slightly out of order, I'm jumping around a bit. Let's control how big the difference between g of x and g of y might be. So by the very design right now, the absolute value of x minus y is less than delta 1. Now this should be red. Delta 1. So absolute value of g of x minus g of y is less than epsilon. Let's now go through these two. What did we use in the next line? We use absolute value of x minus y less than delta over 2 and absolute value of x minus p less than delta over 2. Then we use the triangle inequality to get this.
Is that supposed to be less than for
Which one?
the triangle inequality?
Oh yeah, I guess this, yeah, that's a less than or equal to, isn't it? Thank you. Otherwise it would be just wrong. Okay, so let's sort this out. I think I might have enough time to finish the whole proof. Okay, so let's chase this through. So let's analyze how big absolute value of g of x minus g of p is. And I think the first step is absolute value of g of x is just g of x. Absolute value of g of p is the same as f of p, because p is in u. And let's see, right now, I know that by something really, really high up, I know that f of y is really, really close to g of x. It's within an epsilon of g of x. I also know that f of y is within an epsilon of f of p. So that tells me I'm going to use the triangle inequality, doesn't it? Let's add and subtract f of y and appeal to the triangle inequality. So that's less than or equal to the absolute value of g of x minus f of y plus the absolute value of f of y minus f of p. But that is now less than, epsilon was green, epsilon plus epsilon. Oh, but wait, that's 2 epsilon. And so now you know why I color-coded it so all the epsilons were green. What do you think I need to do with these epsilons? Divide by 2. So I see absolute value. So let's just check that that's actually true. So for every x in u, if absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon over 2. Is epsilon over 2 a positive number still? Yeah, sure it is. And you can stick any positive number you want right there. Like there. So that means absolute value of f of x minus f of p right now is less than epsilon over 2, which is in fact less than or equal to epsilon. So now that step, which just seemed silly, is now just correct. And it looks like I also need this to be an epsilon over 2. Cool. So now I have the absolute, so since absolute value of x minus y is less than delta 1, absolute value of x minus y is less than delta 1 and bigger than 0, then absolute value of f of y minus g of x is less than epsilon over 2. Similarly, right now, since absolute value of y minus p was less than delta, our definition of delta earlier gives us absolute value of f of y minus f of p is less than epsilon over 2. So, do I conclude that the absolute value of g of x minus g of p is less than epsilon? I do. And that happened in both of the cases that we allow for x to be in. So this function g is definitely continuous on the set u. Do you think something similar should happen when x is just a limit point of u? Yeah. And I definitely don't have enough time to fill in the blanks. So I think here's what I'll say instead. Try to compose this proof and be prepared to divide by something once you figure out what you need to divide by. And the epsilons and the deltas. Cool. So, I mean, I guess I should just stop there. Maybe I'll point out that the homework of today is in fact taking corollary 3.7.10, which said that if you have a uniformly continuous function, then there exists an extension onto the closure, and proving that if you start with a uniformly continuous function, if you start with a bounded set and you have a function which admits a continuous extension to the closure, then the function you started with was already uniformly continuous. And the proof won't be heard. So, I mean, I'm going to stop there. Do you have any questions at this point? Okay. So take some time, try to fill in the remaining half of the proof. It'll use exactly the same ideas that we just did, but maybe you'll have to divide by something other than 2. And I mean, I'm really bad at ending lectures, but lecture stuff. And let's hit stop record.